In this video, I will introduce Shapley values. These quantities are a powerful technique for explaining how a machine learning model arrives at its predictions. We will start by covering the motivation for using Shapley values, and then work through the classic mathematical description. To make things more tangible, we will then work through an example in Python. All coding shown in this video is done in a Jupyter notebook, available on my GitHub. You can find a link to this notebook in the description below. So now let's discuss what our motivation here is for discussing Shapley values. So the key element here is to be able to explain model predictions, ideally to the stakeholders of our project. And what we mean by this is that we need to be able to determine what input predictor features are influencing the model predictions. So typically in any machine learning problem, we have a set of input predictor features, and the question comes up, which one of these is influencing the decisions that are being made? And we can imagine that in certain scenarios, this is quite important to our stakeholders. So for example, if we imagine the case of a financial services company and we're building a model to detect financial fraud, we may be required to provide information as to why a certain client was flagged whereas others are not. So that is the main thing that we're driving at here. We want to be able to predict how our models are working. As more data becomes available, we are able to enhance the accuracy of our predictions by using ever more complex models. So more complex models tends to yield better performance, better accuracy. The problem with this is that more complex models are extremely difficult to understand and explain. So we are looking for something to help us get around that issue. Now, one subtlety to this is that whatever approach we adopt, we want it to be general. So that is, no matter what type of model we use, whether it's a linear regression or it's a complicated neural network, the approach that we pick should be able to work and help us determine what is influencing the predictions of that model. And lastly, the technique we use should not only incorporate information that directly relates any given input feature to the output, but also incorporate interactions between the input features themselves. So we can imagine that a very simple and naive way of tackling this problem would be to simply vary one of the input predictor features while holding the others fixed. And we can just vary the single input predictor feature and measure how the output changes. It's a very simple approach, but the problem with it is that we don't capture how the interactions between different input features also affects the result. So we want to have this information also incorporated in whatever technique we use. So it turns out that Shapley values actually meet all the aforementioned conditions. So a Shapley value is something that was originally developed in game theory by Lloyd Shapley, and it has since been adopted within machine learning to then explain how models function. So it's used to determine how the input features influence the output of the model. Now, the properties to the Shapley value that ensure that we assign the correct values to each feature are as follows. So the first thing is that if we find a feature that has absolutely no effect on the output, then its Shapley value will also be 0. And this makes sense. The next property is the efficiency, and this is not the computational efficiency of the Shapley values. In fact, computing Shapley values is quite a difficult challenge in terms of computation. What this means is that if we sum up all the Shapley values for all the different features we are looking at, we will get back to the total value that is represented by that prediction. So that's all that means. The next point is symmetry, and what this represents is that if we have two features that contribute equally to the model output, then their Shapley values will also be the same, will be equal. And lastly, linearity. And what this means is that if we can break up our model into different components, and then for each component, we compute the Shapley values over the features in our data set, then we can sum up all the Shapley values for each model component, and the result of those sums will be the Shapley values for the model as a whole. And this is very relevant whenever we're looking at an ensemble model, such as a random forest or a gradient boosting machine, where in fact the ensemble, the net model, is actually made up of constituent smaller models. And this is a way of treating for that and looking at those sorts of systems. So now let's dive into the classic mathematical description of the Shapley value. So this is it, and at first glance, it can look quite daunting, but stay patient with me. Let's try to take it step by step and look at what all these components are. So phi I here is the Shapley value for feature I. And to compute it, we sum over all the subsets, and the subsets is this capital S, all the subsets of all the features F minus or without the feature of interest that we're looking at, I. So F is the total set of features in our data set, and S is a possible subset. So here we're summing over all possible subsets of F excluding I. Now within this summation we have two terms. The first term here is actually a weight, and these weights are applied to the second term, which is a difference of the value function v. So let's look at each one of these components in turn to see exactly what are they referring to. So here, if we focus in on the weights first, let's just work this out by hand on a sheet of paper, and you can see that I've done that, to get some intuition for what exactly is going on here. So let's imagine a scenario where we have a data set with only 3 features. Those features are labeled 0, 1, and 2. And so that's represented in this array F. Now there are 6 different ways of grouping these features. The key thing that we need to keep in mind here is that we have to assume that the order matters. And so when we talk about possible groupings or ways to collect these features, the order in which they come in matters. Order starts on the left and then goes towards the right. So let's work through an example. I've drawn out here the 6 different possible combinations, so we can start with 0, 1, 2, and then we can go to 0, 2, 1, and so on and so forth, and you get all 6. Now let's imagine that we're computing the Shapley value for feature 1, so I is 1. And the current subset that we're looking at is a subset that just includes feature 2. So now we need to compute a weight for this particular scenario. So what we're looking for here in this list is a situation where we start with feature 2 and then end up with feature 1. And it turns out if we actually look at this, there's only one case where that happens, and that's right at the bottom. We start with feature 2 and we get feature 1 right after it. So the corresponding weight that we have for this scenario is 1 over 6. We can imagine a different scenario. So let's say imagine a case where we have S, our subset, is equal to 0 and 2. Then we need to find all the cases where we start off with 0 and 2 and then end up with 1. And we can see that happens actually here, our second element. We have 0, 2, and 1. But then we also have another example here, 2, 0, 1. That's another possible way of assembling this grouping. And so in this case, our weight would be 2 over 6 or 1 over 3. Now just to make sure that all of this checks out, I actually worked out this formula here just at the bottom for our first example with a subset of just 2. You can calculate that and you actually can see that you get the correct weight of 1 over 6. So you can actually follow this logic and this example to work out all the different weights that are present in this example or any example that you choose. Now the second term is the difference of the value functions. So we can see here that there's actually two different calls to this function v. V is the value function. The first call involves the subset that we are currently looking at, S, together with our feature of interest, I, and we subtract from it another call to the value function that only includes the subset of features S. Now, this function v is itself a difference. Now, in this case, here I've written it out, and what v is going to be is yp, and this is the model output. This is the model prediction for a particular sample of interest, and the sample of interest is this little xs. And we take the difference of this with y hat, which is the expected model output or the expected model prediction. So this is just the mean of the model predictions over the entire data set that we have available. And this construction is fairly typical for machine learning applications. The idea here is that we need a point of reference, and the point of reference that we're going to use is the expected output. And the question that we are aiming to address is why for any particular example in our data, that example is little xs, why do we see the differences that we see with respect to the average? So that's all written out here, and I just emphasize that little xs is an element within big X. Big X, S is the total set of input predictor features. So I hope this gives you some sense of intuition for how the Shapley value is calculated and how it works. Let's now try to make this a bit more tangible by jumping into a Jupyter notebook and work through an example in Python. So now we're in a Jupyter notebook, and like I mentioned before, this notebook is on my GitHub, and I've included a link to it in the description below. So here I've just outlined again the motivation and the definition for the Shapley value that we'll be working with today. So what we're going to do now is create a very simple data set and then implement this equation for the Shapley values, and then work through the example to get a better feel for how all of this works. So let's get started. We can begin by importing all the packages that we need. And now I'm going to make use of the make regression function from scikit-learn to create our data set. And this data set is going to consist of 10 samples with 3 predictive features. So let's go ahead and do that. Now X contains the full set of features that we are going to be looking at. So here we see our set of input predictor features. Each column represents a different feature. And for the sake of this example, I am just going to label them 0, 1, and 2. And now we can also take a look at the labels that we've generated. So okay, I'm going to scale our predictor features so that they have a mean of 0 and standard deviation of 1. So I can use a standard scaler for that. And now my choice of model that I'm going to use is just a linear regression. That keeps things simple. Okay, so now the first function that I'm implementing here is our value function. And so this function takes in as a list our subsets, the subset of features we're going to be looking at, along with the sample of interest. And so that's this xj. This is the sample that we're analyzing, along with the full set of predictor features x and their associated labels, along with the model itself that we're using. And so within this function, if s is not empty, then we train the model on the subset of features that are put in, and then I compute this difference. So I take the model output for our sample of interest, and I subtract from it the expected model output. So if we go back up, this is just this function here for our value function. So that's all that I'm implementing here. So we can run this cell. The next function is called subsets, and this is used to compute all the possible different subsets for a list of predictor features. So this is just going to return a list with all the possible combinations. So we're going to run this cell as well. And now finally we have our final function, Shapley, and this implements our Shapley definition. So in this function, we are just implementing this equation. So what we do here is, again, as input, we have our sample of interest that we're analyzing along with the feature we're looking at, then our data, x and y, and then our model. So what we do first is we compute, or we collect all the different features that we have in our data, we count them, and then I remove feature I from this list. This is our feature of interest that shouldn't be included. And I initialize the Shapley value to 0. And then for all the different subsets, so I'm just going to loop over all the subsets of f. We then count the size of the subset. I compute the weight. That's the first term in our Shapley definition. And then I compute the difference in the value function here. And this is the second term in our Shapley definition. And finally, then we just add the product of these two terms. We add this to our variable phi. We iterate over all the different subsets, and then finally return the result that is produced. So I can just run that cell. And now we can work through a simple manual example to get a feel for how all of this works. So the sample that I'm going to want to analyze is the second row in X. So here I'm just calling this X1. We can extract this out. And now let's run our Shapley function for each of the features that we have in our data. So we'll start with feature 0. And here we can see that we get a Shapley value just over 3. We can get the Shapley value for feature 1. And here we have a much bigger value, over 93. And we can do the same thing for feature 2. And here we got a smaller value, just over 2. And looking at this, we can see right away that for this particular sample, it's feature 1 that's primarily driving the model in its output. By far, it's the one that has the most influence for the prediction that was made by our linear model. So that's something that we can immediately get out of these results. We can plot this to make it a little bit more easier to see. And we have this here. Again, this bar plot just shows that feature 1 clearly dominates over the other 2 features for this sample. Now, just to verify that our implementation is done correctly, we can do a simple check. We can sum over all the different Shapley values that we've just computed. We can do that by running this cell. And now we can compare this with the difference between the model output for our sample of interest and the expected model output. So this is essentially the same as our value function, but now for all the features within our data. So let's just run this. And we can see that these 2 values are the same. So this is really good. It demonstrates that we've implemented things correctly. So this is nice. We can now carry this a bit forward and compute the Shapley values for all the samples in X. So far, we've only looked at one sample, but there's no reason why we can't extend this and compute it for all 10 of the samples that we have. So I can just run this cell to do that. And now let's plot the results. So okay, here we see the Shapley values that we get for all the different samples, and for all the different features that we have in our data. Now, the larger the absolute value we get for the Shapley value, the more influential that feature is. So we can see right away that feature 0 is kind of broad, right? It ranges over quite far on the x-axis, but the frequency isn't too high. We have counts mostly of 1. There's a couple cases where it has 2. Feature 1 has 3 peaks. It has one peak that's somewhere around 20. That's quite high. But then it has these 2 other peaks that are way out in the wings. And these indicate the presence of very large Shapley values. And so looking at this plot, it's easy to see that probably feature 1 is the most influential here. And finally, feature 2 produces values, but they all cluster around 0. So the result of looking at this plot, it would seem to indicate that for our model, feature 1 should be the most important for driving how our model behaves. Feature 2 should be the least important, and feature 0 is somewhere in between. So we can take a look at that and actually try to see it in a completely independent way. by looking at the model coefficients. Now, because I normalized the input predictor features, we can actually carry out this analysis. With linear regression, the importance of the feature should be related to the magnitude of its coefficient. So let's take a look at that. And here we can see, indeed, that these two match up. So feature 0 has a value of 33. Feature 1 has a value of 54. And feature 2 has a value just below 12, so it's 11.7. And this corresponds with what we've seen in the plot. So feature 1 is the most influential, feature 2 is the least influential, and feature 0 is somewhere in between. So this all matches up, and it's a pretty nice example. So I hope that gives you some intuition for how Shapley values work and how we can interpret them. So what's wrong with this approach that we've done so far? Well, everything we've worked with right now involves the classic Shapley value. Again, this was developed for game theory. The two problems are, one, we had to iterate over all the subsets of our set of predictor features. And for a very large data set with many, many features, this just becomes impossible to do. The number of possible subsets grows exponentially as the number of features we have also increases. So this presents a big problem for us in terms of computation. The second problem we have is that we actually had to retrain our model each time we made a call to the value function. And in reality, this just doesn't make much sense. For one thing, many machine learning models just won't work on a subset of features. And secondly, the training times for many complex models is just, it's very long. And so doing that repeatedly just makes this approach untractable. Like we just can't do that. For these reasons, in practice, approximate Shapley values are computed using sampling methods like Monte Carlo. In my next video, I'll explore these techniques. If you enjoyed this content, please like the video or subscribe to the channel. If you would like to learn more about machine learning in general, please visit my site, insidelearningmachines.com. I have a link to my site in the description below. Have a great day, and see you in the next video.